Okay, so we discuss motion in one direction. We say motion in one dimension. So all the examples we discuss, the motion is horizontal, like driving a car on a horizontal straight road, or somebody walking along a straight road. And then we discuss terms like displacement, velocity, acceleration, and how all these combine with time, how to solve kinematic problems. So we talk about the four equations, the four kinematic equations. So these equations, we can apply them the same way we use them in horizontal motion. We can use these equations in vertical motion as well. Vertical motion means it's like something falling from a height. Like, let's say you go to a top of a building and you drop something from the top of the building. So it's a free fall. We call it these kind of motions, we call them free falls. It's falling under gravity. So let's look at a simple diagram. So this is the Earth's surface, and here let's say there's a building. Oops, it's kind of crooked. That was not my intention, but okay, let's add a kind of bridge kind of thing. So you are on top of this. Here you are, and then you have this a tennis ball in your hand, and you're gonna drop this. Now when you release it, what happens? This object, starting from initial velocity of 0, it's gonna fall down. And what kind of motion is this? If you just release it, if you just let it go, it's gonna start from 0, but the speed is going to increase. Why? The Earth underneath, Earth here, has something called gravity, gravitational attraction. Gravitational attraction. Gravity, or the gravitational attraction, is a pulling force acting on any kind of mass. It's special, it's specifically towards masses. It's pulling on mass, right? This tennis ball has a mass, couple of grams, half a kilogram. I don't think a tennis ball is that heavy. Anyways, mass is measured in grams or kilograms. What's the definition of mass? Anybody remember? It's the amount of matter, right? In very simple terms, the amount of matter. We use the letter M to indicate mass. This is the letter symbol for mass. Measure it with kilograms. This is the standard units. So this is the symbol, this is the unit, and the quantity, or let's say just the term. Term is mass. The symbol we use is little m. The measuring unit is kilograms. In addition to that, we have grams, milligrams, micrograms. Especially in biology and chemistry research, you will be working with very, very small mass amounts. And then we have the British units, lbs, which really not very useful when it comes to scientific studies, but these are again acceptable measuring units. All right, so coming back to the topic, let's say this tennis ball has a mass of m equals 200 grams. So this mass is being pulled by gravity underneath. It's being pulled towards the earth. That pulling force creates this force on the tennis ball. We call it the weight. Weight is something. Weight is a force. It appears only if the object is in a gravitational field, right? Weight doesn't have any meaning if you are not closer to a gravitational field. If you go far away from Earth, like outer space, like here's the Earth here, you are here on the Earth's surface, you have the feeling, the influence of weight. But if you are here in a like a spaceship, right, and if you are inside, if you are very far away from this gravitational field, you might not have the feeling of weight. You still have the mass, that doesn't change, but in order to have a weight, you have to be in a gravitational field. So coming back to the topic, the tennis ball is up here, you drop it, Earth is pulling on it. Because of the gravitational attraction, it's gonna accelerate. Now here's the thing, when it comes to these kind of free falls, now this is a free fall. What is a free fall? Who's giving this acceleration? In previous examples, where you have a vehicle accelerating over the road, along the road, right? The acceleration came from the engine. The engine is producing enough force to increase the speed. But here, acceleration is coming because the Earth is pulling on it. So the free fall acceleration is always a constant. It's always 9.81 meters per second squared. This number is unique to our Earth, near to the Earth's surface. When you go away from the Earth's surface, it decreases. Like over here, it's 9.81. But if you are up here, like let's say a couple of kilometers above the surface, up here it'll be something less than that, probably like 7 meters per second squared. If you're up here, it'll be even less, maybe 2, and then you go here far away from the Earth, it drops to 0, right? So this number is unique to the Earth, and the number is 9.81 for all our calculations, because when you talk about a tall building or whatever, it's still very close to the Earth's surface. If you go to a different planet, like for an example, on the surface of Moon is being a smaller planet, the gravity is also small. So later we will talk about how to figure out the gravity of a planet. So the Moon has roughly about 1/6 of this. So it has a smaller gravity, about 1/6 of Earth. Think about something like Jupiter, like a huge planet. It has a huge gravity. That pulling force is so high, you can't even stand on top of it. You get pulled down so hard to the surface, you get like crushed, which is really bad. So you're not gonna go there. Alright, so coming back to our topic. We kept going away from the topic a couple of times. So let me erase all these distractions real quick. Okay, so you drop something from a height, initial velocity 0, it's going to accelerate at 9.81. When it comes to free fall problems, either you drop something from a height, or you throw something down from a height, or you can throw something up, straight up. The acceleration it feels is this, and we denote it by the letter G to indicate its gravity or the gravitational attraction. So this thing's gonna fall on the way the speed is increasing. So we can try to calculate things like what's the speed just before hitting ground, v final, what is that? There's no point of asking what's the speed after hitting the ground, because it hits the ground and it comes to a stop, so it's always 0. So what we are interested is what is just before hitting ground, right? And then things like how much time it takes. So for an example, if we know the height of this building, maybe like 50 meters or whatever, this height, right? This is your x falling down. So we can calculate these things like how much time it takes, what's the final speed, and all sort of things. We're going to use the same equations. Remember this one, v final equals v initial plus at. Now we're going to write this equation downwards. Initial velocity, final velocity, this will be replaced by 9.81. So instead of getting into more details, let's try 1 or 2 examples. Alright, let's see. Let's go back to the PowerPoints. Okay, the first example says falling from a tower. Suppose that a ball is dropped with a 0 initial velocity from a tower of 70 meters high. How far will it have fallen after time t equals 1 second, t equals 2 seconds, t equals 3 seconds? It says ignore the air resistance. Okay, so I am going to redraw this diagram, make it a little more clear. Okay, so here we have I am really having a hard time drawing this straight line, so let me try one more time. Alright, yes. Okay, here's the building, which is 70 meters tall. So you are here at the top, you're gonna drop this thing. V initial is 0. Acceleration is 9.81, pointing downwards. Question is, after 1 second, so questions, find the distance at t equals 1 second. Okay, so for these kind of problems, for any kind of problem, we need to define our starting point. Now if it is a vehicle moving on a road, we have a starting point. We define an origin. This is where we start, this is the starting point, this is where we're going to measure the distance from. Same thing here. If you drop something from a top of a building, it's a good idea to take your starting point as the top of the building. So first thing is define a starting point. In this case, top of the building. Now if the problem says you're gonna shoot something straight up from the ground, then the ground will be your starting point. So based on the problem, we have to define our starting point. So So then from that point the ball is moving, I'm trying to draw an arrow here, moving downwards with an increasing speed, so your acceleration is positive 9.81, right? It's not slowing down, it's speeding up, so it's going to be a positive acceleration. V initial is 0. The question is, what's the distance after t equals 1? After 1 second, what's the distance it had traveled? So what can we do to find the distance? Think about the equations we have. So I'm going to write them over here. V final, V initial plus AT, x equals VIT plus half AT squared. V final squared equals V initial squared plus 2AX. This is I. So out of these three, right, this is 1, 2, 3. Since I'm trying to find the distance, my question is, what is x? As I'm trying to find distance, I believe number 2 is going to be the best option. So I'm going to start with number 2. Distance equals VIT plus half AT squared. Here's an advice. Whenever you guys work on these problems, always write the equation first. Instead of plugging numbers, just write it down. When you do it couple of times, automatically you will remember the equation. This is guaranteed. This is how I remember these equations, because I keep writing them. Alright, so x equals v initial 0, time is 1 second, plus half times gravity. It's positive because the speed is increasing, we can take it as a positive 9.81 and 1 squared. So it's going to be 0 plus half times 9.81 times 1. 9.81 times half times 1, this is going to give you 4.95 meters. After 1 second, it's going to be somewhere here, 4.95. Oops, that's not right. Okay, right. So let me try a different color. This distance right here is 4.95 meters. Alright, so there's 2 more questions. Find the distance when time equals 2 and 3. I want you guys to try that. I'm going to add a question. Total time, or in other words, how long it takes to hit the ground. Another question, number 4. Final speed. What is the speed when it hits the ground? So let's give a try how to find these. So I'm gonna make some space here. Alright, total time. So let's see things we have in hand. V initial 0, acceleration 9.81. Total time means that it has to fall a total distance of 70 meters, right? How long it takes to cover this distance. So by looking at the equations we have in hand, I am going to use equation number 2. X equals VIT plus half AT squared. 70 equals V initially is 0, so regardless of what the time is, it's going to become 0. Half times 9.81 times, let's see, SpaceX Mars rover. Alright, it's tomorrow. 9.81 times squared. Okay, so we have 70 equals half times 9.81 is 4.95. Let me double check that just in case. 9.81 divided by 2 is 4. Oops, it's 4.9. It's not 4.95, it's 4.9. So there is no 5 here. There is no 5 here. 70 equals 4.9 times t squared. So what is t squared? T squared is 70 divided by 4.9 divided to the other side. So t equals square root of this answer. Hmm, 70 divided by 4.9. 70 divided by 4.9 is 14.2. So where is it? 14.2, and square root of 4.2. Oh, I'm sorry, 14.2. We have 3.76. So that means this thing will be falling for 3.76 seconds before it hits the ground. That's your answer. Okay, last question. What's the speed just before hitting ground? So I'm gonna make some space here. I'm gonna erase some of the stuff. So let's erase this. Alright. Question number 4. Final velocity. So you can use either equation 1, it has final velocity, or you can go with equation 3, that also has final velocity. I'm gonna go with 1. Initial plus t0 9.81 times the time. We just found out that it takes 3.76 seconds to hit the ground. So what's the final speed? Multiply by 9.81, 36.96 meters per second. Right here, just before hitting ground, right here, 36.96 meters per second. Okay, so this is how you solve a problem with free fall. Now you can do the same thing. I can ask a question in the opposite way. So let me erase this. Let me clear this. Alright, think about a situation like this. You are on the Earth's surface and you have some kind of like a cannon or something where you can shoot things straight up, or it could be a fireworks kind of stuff, So you're gonna, let's say you're just throwing a baseball straight up, going up like this. In order to do this, you have to have a good initial velocity, right? So your V initial, now it's not 0 anymore. You can't start something with 0 and expect it to go up unless it's gonna be something like a rocket ship or some propelled object. If it is something you give it a speed and expect it to continue, you have to give it some good initial speed. So you have to give some initial speed, let's say 30 meters per second. The question is how far it's gonna go. So this thing is gonna go up. On the way up it's gonna slow down, and then once now the speed is decreasing, right? 30, 25, 20, 15, 10, 5, like that. Once it becomes 0, that's the turning point. It's going to turn around and then come back again, increasing the speed on the way down. So on the way down, speed increases. Now there is an interesting thing. If we consider there is no air resistance, atmosphere is something that always slows things down. On the way down it slows you, on the way up it slows you. Atmosphere is a big resistance, but for these kind of problems we don't need that much sensitivity, so we can assume that atmosphere's resistance is kind of not that significant to the accuracy we are looking at. That's reasonable. So without these resistive forces, this problem is interestingly very symmetric. That means you start with 30, it comes back just before hitting the ground, it comes back to 30 meters per second. It's symmetric. If it takes, let's say, so many seconds, 5 seconds to go up, it will take the same 5 seconds to come back. At any given point, let's say at this point the speed going up is let's say 10 meters per second. At the same height level, the speed that it's coming down is also 10 meters per second. So everything has symmetry in these cases. Alright, so let's try this problem. We're gonna shoot something straight up. So question number 1, how high it goes. Number 2, how much time it takes to reach the top. Question number 3, how much time it takes to come back. This little comma signs means I'm repeating the same words. Alright. Okay, 3 questions. So how do you solve this? Let's write down the information we have in hand. This time we are going up. V initial is 30. It's not 0. You can't say it's 0. Alright. Acceleration. Now this is our starting point. The ground level is our starting point. Right. So from this point, when you look up, when you write this equation, you see that speed is decreasing. On the way up, it's slowing down. So what kind of acceleration is this? It's still gravity. It's still 9.81, but negative 9.81. On the way up, it's gonna be negative. We don't know the distance, we don't know how far it's gonna go, we don't know how much time it takes, so x is unknown, t is unknown. We do know one thing, we know that final velocity at the very top has to be 0. That's why we say that it's the turning point, because velocity becomes 0. If there is some velocity, it's gonna keep going, right? So when we consider the very top point, velocity is 0. Okay, so considering all these, v initial, v final, acceleration, I think the easiest thing to find is the time. So I'm gonna start with the second question. v final, v initial plus at, 0, 30 plus negative 9.81 times time. What's the time? Time equals, so this negative, when you take it to the right hand side, so if I write another line, this gonna be 0 equals 30 minus 9.81 t. I'm gonna take it to the other side. I have positive 9.81 t equals 30. So t equals 30 divided by 9.81, which is something like 3.1, I think. See for sure. 30 divided by 3.058, so approximately 3.1, but let's say 3.06 seconds. It takes 3.06 seconds to go up. So now I'm gonna work on the first problem. How high it goes. So I'm gonna use what can I use? I can use the second equation, x equals vit plus vt squared. I can use this, v final squared equals v initial squared plus 2ax. I'm actually gonna go with this one. This looks easy with in terms of numbers. V final is 0, so I'm not going to use this. V initial 30 squared 2 times 9.81, which is negative, times x, the distance. So I have 0 equals 900 minus this thing, so 2 x equals 900 divided by 19.62. Oof, 45, 46, 45.87. It's gonna go 45.87 meters. This height up here, 45.46 meters from the ground. Question number 3 is asking total time. You don't have to do any math. We know the time to the top, so the total time is t is 2 times 3.06, which is 6.12 seconds. Okay, so there's few more problems. I want you guys to give them a try, and then we can discuss these next time when we meet. All right. Okay.